For reactions that are not carried out at standard state conditions, the change in free energy can still be calculated. For example, if you run a reaction at any temperature other than 298 Kelvin, we might want to figure out what delta G is to say if the reaction is going to be spontaneous or non-spontaneous. This is kind of an estimate, and we can use the fact that the enthalpy and entropy changes, so delta H and delta S, do not change much with temperature. So we can use those standard enthalpy and entropies to give an approximate delta G just by changing the temperature in our equation. Delta G naught at a different temperature, so sub T, is approximately equal to the enthalpy at 298 Kelvin, or the standard enthalpy, minus the temperature in Kelvin, times the standard entropy at 298 Kelvin. So our standard entropy and our standard enthalpies can either be given to us or those could be calculated by using the large tables. At 298 Kelvin, the Gibbs free energy is equal to positive 5.40 kilojoules for the reaction N2O4 going to 2NO2. So at this temperature, the reaction is non-spontaneous because we have a positive value for our delta G. We're also given our enthalpy of 59.7 kilojoules and our entropy of 177 joules per Kelvin. What is the value of Gibbs free energy at 398 Kelvin? So now at a different temperature. The Gibbs free energy at 398 Kelvin, so the temperature specified, will be equal to the delta H at 298 Kelvin minus the temperature in Kelvin times the delta S at 298 Kelvin. So we're going to substitute those values in. Delta H is 59.7 kilojoules minus our temperature is already given to us in Kelvin, so plug in 398 Kelvin, times our entropy. Our entropy we should convert to joules per Kelvin so it matches our enthalpy. That would be 0.177 kilojoules per Kelvin if we divide by 1,000. This is an estimate of what the Gibbs free energy would be at 398 Kelvin, and it comes out to negative 10.7 kilojoules. Notice now when we raise the temperature of this reaction, we got a negative value, and therefore that means this reaction is now spontaneous at 398 Kelvin. The reaction mixture will determine which way it proceeds to attain equilibrium, as well as delta G. When we looked at our free energy diagrams, the reaction always proceeded in the direction minimizing the free energy, or heading towards equilibrium. The sign and the magnitude of Gibbs free energy determined that position of equilibrium, whether it was reactant favored or whether it was product favored. The direction a reaction proceeded depended upon where the reaction mixture composition standed relative to the free energy minimum, so it always headed towards that equilibrium composition where delta G was equal to 0. And the reaction only proceeded spontaneously in the forward direction if it led to a lowering of that free energy. So if a reaction was spontaneous in one direction, it was going to be non-spontaneous in the reverse direction because you would have been heading to a higher free energy change, which is not favorable. It always will head to a lowering of that free energy. Delta G can be calculated at non-standard state conditions when a reaction is not at equilibrium and we do not have an equilibrium mixture. Delta G, notice there's no naught, will be equal to delta G naught, so at standard state conditions, plus RT times the ln of Q. Recall that the ln of Q was called the reaction quotient. The reaction quotient represented the equilibrium mixture at non-equilibrium values. So it's still calculated the same way as K sub C, where we had products over reactants, but we plugged non-equilibrium concentrations into it. When we see delta G without that superscript naught, that represents the free energy change under non-standard state conditions. Delta G with the naught symbol represents the free energy change under standard state conditions. Temperature always has to be in Kelvin. R is the gas law constant, 8.314 joules per Kelvin times mole. And Q is our reaction quotient. Could be QC or Q sub P, meaning concentration or partial pressure, depending upon what type of reaction it is. Calculate the free energy change for ammonia synthesis at 25 degrees Celsius given the following partial pressures: 1 atm of N2, 3 atm H2, and 0.0 atm NH3. So we were given these partial pressures, but nowhere does the problem say that these are equilibrium partial pressures. So we must have to use Q sub P because we don't know that those are at equilibrium. What direction must the reaction proceed at 25 degrees Celsius to reach equilibrium? Our Gibbs free energy is given to us where we have our naught symbol, so that's our standard Gibbs free energy. The equation we're going to use is delta G is equal to delta G naught plus RT ln of Q. So first we should calculate Q and then substitute everything back into our equation. So Q will be equal to the partial pressure of our product, so the partial pressure of ammonia squared over the partial pressure of our reactants, partial pressure of N2 times the partial pressure of H2, and that one would be cubed because there's a 3 out in front of the hydrogen and a 2 out in front of the ammonia. So don't forget to square or cube or raise your partial pressures to the coefficients from the balanced equation. Next, we can put in our partial pressures that were given to us, our non-equilibrium partial pressures. We have 0.02 atmospheres on the top, and that'll be squared. For N2, we had 1 atmosphere. And for H2, we had 3 atmospheres. And that was cubed. Our value for Q, when we calculate it, our reaction quotient, comes out to being 1.5 times 10 to the negative fifth. So now we can substitute that value of Q into our equation to get at our delta G at non-standard state conditions. Delta G will be equal to our Gibbs free energy in the standard state conditions, which is negative 33 kilojoules, plus R, our gas constant, which is 8.314 times 10 to the negative third kilojoules per mole times Kelvin, converting joules into kilojoules. That's why we have 10 to the negative third, times our temperature. We were told 25 degrees Celsius, which in Kelvin is 298 Kelvin, times ln of Q, and we just calculated Q to be 1.5 times 10 to the negative fifth. When we calculate our delta G at non-standard state conditions, we get negative 60.5 kilojoules per mole. Notice our Kelvin will cancel, and simply we're going to be left with kilojoules over moles. Sometimes the mole is not introduced and people will just say delta G is listed in units of kilojoules. So whether you say kilojoules or kilojoules per mole, it's essentially the same thing. And we have a negative value out front of our delta G, so this tells us the reaction is going to be spontaneous at these non-standard state conditions. So that means that when we have the given partial pressures that the equation gave us, that this reaction will proceed in the forward direction to reach equilibrium. Or in other words, it'll proceed to the right and make more ammonia, and some of the nitrogen and hydrogen will get used up. Calculate the Gibbs free energy for the formation of ethylene, C2H4, from carbon and hydrogen at 25 degrees Celsius when the partial pressures are 100 atm hydrogen and 0.1 atm of ethylene. The standard state Gibbs free energy is 68.1 kilojoules per mole. So what would our equation be for the formation of ethylene? We would have 2 moles of carbon, which is a solid, reacting with 2 moles of H2, which is a gas, to give us C2H4, or the ethylene, which is also a gas. Our Gibbs free energy at the standard state was given to us in this problem, and now we have a balanced equation in order to calculate our Q as well. So we have the same number of moles of carbon on the left and right hand side, and we have the same number of moles of hydrogen on the left and right hand side. Our Q will be equal to the partial pressure of our ethylene, C2H4, over the partial pressure of our hydrogen, which will be squared. Remember, we don't include solids or liquids in our equilibrium or our reaction quotient expressions, so we don't have to worry about the carbon. We can take our partial pressures for ethylene, which was 0.1 atmosphere, over our partial pressure for hydrogen, which was 100 atm squared, to get our Q value. Q comes out to about 1.0 times 10 to the negative fifth. Next, we're going to want to use the equation for calculating Gibbs free energy at non-standard states. Delta G will equal delta G naught plus R times T times ln of Q. We've got our delta G naught, 68.1 kilojoules per mole, plus R, which is our gas constant, 8.314, and we'll put it in kilojoules times 10 to the negative third, kilojoules per mole times Kelvin, times our temperature. The reaction was ran at 25 degrees Celsius, so our T will be 298 Kelvin. And lastly, times ln of Q, which will be ln of 1.0 times 10 to the negative fifth. Our Gibbs free energy at the non-standard state conditions comes out to being 39.6 kilojoules or kilojoules per mole. Either one is fine. And we got a positive value for our delta G. So this means that the reaction is non-spontaneous, as written, and therefore it'll proceed in the reverse direction, or essentially from products to reactants. It'll proceed left to be spontaneous. So the direction that the reaction will head to reach that free energy minimum will depend upon the sign of delta G. If it's non-spontaneous in the forward direction because we got a positive delta G, then that means it must be spontaneous in the reverse direction, or in the products to reactants direction. We can also relate our thermodynamic equation for delta G back to our equilibrium constant K. We learned that Gibbs free energy, the non-standard state Gibbs free energy, is equal to delta G naught plus RT ln of Q. But at equilibrium, delta G is equal to 0, we learned, and Q, the reaction quotient, is equal to K, the equilibrium constant. So we can substitute 0 in for delta G and K in for Q. So this would become 0 equals our delta G at standard state conditions plus RT times the ln of K now. We can rearrange around our equation by moving our RT ln of K term to the other side, and that gives us delta G naught equals RT, negative RT, times the ln of K. K is the thermodynamic equilibrium constant. It could either be K sub P when we have gases, or K sub C, meaning concentration for our solutions. R is that same gas constant, 8.314 joules per Kelvin times mole. And our temperature has to be absolute temperature scale in Kelvin. For the reaction, 2 moles of NO gas plus 1 mole of O2 gas forming 2 moles of NO2 gas, we are given our Kp 1.7 times 10 to the positive 12 at 25 degrees Celsius. And this is a big value for K sub P. And remember that a big value told us that it was a product favored equilibria. So that should mean at equilibrium, we have more products than reactants due to having a large value for the equilibrium constant. What is delta G sub naught for the reaction in kilojoules per mole? So our equation when dealing with the equilibrium constant and delta G is delta G naught equals negative R times T times the ln of K. We simply have to substitute everything into our equation. Our R is going to be 8.314, and I like to convert it into kilojoules, times 10 to the negative third kilojoules per mole times Kelvin. Our temperature in Kelvin, it will be 298 Kelvin because we had 25 degrees Celsius, times the ln of our equilibrium constant, 1.7 times 10 to the 12th power. And for our Gibbs free energy, we're going to end up with negative 70 kilojoules per mole. and we got a negative value for our delta G. So this tells us that the reaction is spontaneous as written at our temperature that we used, and so it'll proceed in the forward direction from reactants to products to head to that free energy minimum. And so from the equilibrium constant value, that K sub P, we also would have predicted that it was a product favored equilibria just due to it having a large size. So those two kind of correspond to one another, that sign on the Gibbs free energy and the magnitude of the equilibrium constant. Let's try another one. Calculate the equilibrium constant for the synthesis of methanol at 25 degrees Celsius. CO2 gas plus 2H2 gas forms CH3OH, which is a liquid, and that would be our methanol, the CH3OH. Gibbs free energy at 25 degrees Celsius in standard state conditions is negative 29 kilojoules per mole. So we're going to use our equation that relates the equilibrium constant, delta G naught equals negative R times T, ln of K, and this time we're solving for just K alone. We want to find that equilibrium constant. So we could rearrange and say that ln of K is equal to delta G naught divided by negative R times T. So first let's solve for what ln of K is equal to by substituting our values in. Gibbs free energy is negative 29 kilojoules per mole over negative R 8.314 times 10 to the negative third kilojoules per mole times Kelvin. And our temperature is going to be 298 Kelvin. So our ln of K comes out to being 11.7. And to get K, we have to undo the natural log function. And to undo the natural log function, we use the E function. So E to the ln of K will equal E raised to the 11.7 power. E to the ln of K will just end up equaling K. So we can find K by taking E raised to the 11.7 power, which gives us 1.2 times 10 to the fifth as our equilibrium constant for this reaction. And once again, we got a big value for our equilibrium constant. And so that corresponds to our delta G, which was negative. So that was spontaneous in the forward direction. Next, let's try a problem that combines a couple things. For the reaction NO2 plus NO forming N2O plus O2, we have our non-standard state Gibbs free energy at 1,273 Kelvin, or 1,000 degrees Celsius, is negative 9.67 kilojoules per mole. A 1 liter vessel at 1,000 C contains 0.02 mole NO2, 0.04 mole NO, 0.015 mole N2O, and 0.035 mole O2. Is the reaction in equilibrium? So yes or no first. If not, what direction will the reaction proceed to reach equilibrium? So there's a few things we want to find first. We want to find Q, our reaction quotient, and we're going to eventually want to compare that to our equilibrium constant K. In order to find K, we're also going to need to calculate or find our Gibbs free energy at standard state conditions. So our Q will be equal to, or our Q sub C, since we were given molar concentrations in 1 liter, so molarities, will be equal to the concentration of N2O times the concentration of O2, our products, over the concentration of our reactants, NO2 times NO. So our moles are essentially equal to our molarity since we're in a 1 liter vessel, and we can substitute the moles right in. For N2O, we have 0.015 molar. For O2, we have 0.035 molar. For NO2, we have 0.02 molar. And for NO, we have 0.04 molar. So calculating our Q value, our reaction quotient, we come up with 0.656. So right off the bat, that doesn't tell us much of anything. We don't know if the reaction is in equilibrium or not yet because we don't know what our K value is to compare our reaction quotient to. Now we can use delta G is equal to delta G naught plus the RT times ln of Q in order to solve for our Gibbs free energy at standard state conditions to later use that when we want to get K. Since we know Q and we know everything else, we know our delta G at non-standard state conditions, we can find delta G naught by rearranging. So delta G naught will be equal to delta G minus RT times the ln of the reaction quotient. And we can substitute everything in. Delta G is equal to negative 9.67 kilojoules per mole minus R, which is 8.314 times 10 to the negative third kilojoules per mole times Kelvin. Our temperature is 1,273 Kelvin times the ln of our reaction quotient 0.656 for our Q. This gives us a delta G at standard state conditions of negative 5.21 kilojoules. And so we got a negative value here as well, which means that at standard state conditions, the reaction should be spontaneous in the forward direction. This value would be the Gibbs free energy for all of our gases if they were at 1 molar solutions or 1 atmosphere for their partial pressures. And that's not what we have right now. So that's why our delta G on the top does not exactly match this delta G. Next, to find our equilibrium constant, we can use the equation delta G naught equals negative R times T times the ln of K. We can rearrange for the ln of K by saying delta G naught over negative R times T. We calculated delta G naught on the previous slide, and it was negative 5.21 kilojoules. Then we have on the bottom negative R, which is our gas law constant, 8.314 times 10 to the negative third kilojoules over moles times Kelvin, times our temperature in Kelvin, which is 1,273 Kelvin. This gives us an ln of K equal to 0.492. To get K alone, we want to take e to the ln of K and e to the 0.492, which gives us our equilibrium constant of 1.64. Now we can compare our K value to our Q value. Just a reminder, Q we calculated previously as 0.656. So in this example, Q is less than K, and so the reaction is not in equilibrium because they're not equal to one another. And when Q is less than K, that means that Q has to become bigger. And remember, Q is a ratio of the products over the reactants. So if we want Q to get larger, we want our numerator to increase. So therefore, that must mean the reaction will have to shift to the right or towards the products to create more of them. Also, when we look at the value of delta G, that's a negative 9.67 kilojoules that we were given initially. That negative value also gives us a hint that the reaction should shift right towards equilibrium because it's spontaneous in the forward direction.